Hello, this is Geometry 9.3, Similar Right Triangles. I'm going to go through the theorems kind of quick for the similar right triangles because I'm going to show you a little trick that you could use instead of having to remember what each of the theorems states. So the right triangle similarity theorem states if you have a right triangle, so I'm going to redraw it, right triangle ABC, remember, and then this will be especially important and true once we start trigonometry. But if you have a right triangle ABC, you always want to make C the right angle. But in a right triangle, if you have an altitude drawn from the right angle, so the altitude's the height. Basically what happens there is that altitude creates three similar triangles. And if I label that altitude D like it is here, the three similar triangles are your original triangle, triangle ABC. Okay, that's a right triangle. Triangle ACD, and then triangle CBD. All of those triangles are similar. So you have three similar triangles if you create an altitude from the right angle of a right triangle. That's what the right triangle similarity theorem states. And before we go over the last two theorems, you need to know what a geometric mean is. So a geometric mean of two numbers, A and B, if it's x, then you could always set up this proportion. A over x equals x over b. So what that means is if you cross multiply, a times b is equal to x times x. And if you solve that for x, you take the square root of each side. The geometric mean between two numbers, a and b, is the square root of the product of those two numbers. Let me give you an example. If I want to find the geometric mean between 9 and 4, I could set up this proportion. So 9 could be A and then 4 could be B, or the other way around. It doesn't really matter. So 9 over x equals x over 4. And then I could cross multiply. 9 times 4 is 36. That's equal to x times x, which is x squared. Take the square root of each side. X is 6. Maybe the quicker, possibly easier way to do that, sorry you couldn't see that, is take the product. 9 times 4, it's still 36. And then the square root of that is 6. So that's the geometric mean between two numbers. And then theorem 9.7, the geometric mean, or it's also referred to as the altitude theorem. If you have a right triangle, the altitude from the right angle divides a hypotenuse into two segments. So here's what I'm going to do. Those two segments, here's the altitude. It divides this hypotenuse into two segments. I'm going to let this segment, AD, be x, and then the segment DB be y. It says the length of the altitude, okay, is the geometric mean of the lengths of the two segments of the hypotenuse. So I'm going to let the length of the altitude be x. Sorry, I already let this be x, so I'm just going to let it be a. Then this altitude is the geometric mean between these two parts. So I could set up x over a equals a over y. And then if I wanted to solve that, cross multiply. A squared is equal to x times y. And that's really what we have here. X, I let be AD, y is dB, and then CD, I let be A. But that's the geometric mean, or the altitude theorem. And then theorem 9.8, the geometric mean, or the leg theorem. In the right triangle, you have the altitude drawn to the hypotenuse. Again, it divides a hypotenuse into two parts. I'm going to let those be x and y, but what the geometric mean leg theorem states is the length of each leg of the right triangle. So CA, I'm going to let that be P. CB, I'm going to let that be Q. But the length of each leg is a geometric mean of the lengths of the hypotenuse and a segment of the hypotenuse that is adjacent to the leg. Okay, that's kind of a mouthful, but what that means is this leg right here, CA of the original right triangle, is a geometric mean between the hypotenuse. So that would actually be x plus y. If P is a geometric mean, then it's a geometric mean between x plus y and then the adjacent part or segment of a leg. So here's P, the adjacent part or segment would be x. So that's a proportion that you could set up. And then the same thing is true for the other leg of the original right triangle, what I call Q. Q is a geometric mean. So I could start setting them like this, between the entire hypotenuse in this case, x plus y, and the adjacent segment is y. Really, these are the same things as what I just set up. It's just using each of the segment lengths in terms of the endpoints instead of single variables like I have. And then instead of x plus y, it's AB here. Because AB, if you noticed, is x plus y. But I'll show you in the next part a quick, possibly an easier way, but a little trick instead of having to set up these somewhat complex theorems in order to find missing side lengths of right triangles.